The flow of materials, whether cars in a highway, liquid through a funnel, or electrical signals within a circuit, depends on the capacity of the medium to handle the amount of traffic. In electronics, this capacity is referred to as bandwidth. It defines the usable frequency range of a device. Bandwidth is a key specification in both analog and digital systems. It is an important factor to consider when selecting an electronic component. In analog signal processing, bandwidth is the difference between two frequencies at the lower and upper boundaries of a continuous set. It is typically quantified in hertz. Bandwidth specifies a medium's ability to process various frequencies. Ideally, a signal with a frequency that lies in the specified range passes through the medium without a significant amount of amplitude reduction. On the other hand, frequencies outside the bandwidth range experience an amplitude loss. Generally, the amplitude reduction is specified in dB. Most often, bandwidth specifies the frequency at which the processing loss is 3 dB or about 30% of the input signal. Baseband and passband terminologies describe the lower frequency boundary for a given bandwidth. In a baseband system, the lower boundary is 0 Hz or DC. And the higher boundary is referred to as the bandwidth of the system. Therefore, signals with frequencies less than the bandwidth pass through the system without a significant amount of loss. Operational amplifiers and oscilloscopes are examples of systems for which a baseband bandwidth specification is more meaningful. For a passband system, bandwidth defines a frequency range around a midpoint called the center frequency. The two cutoff frequencies are the center frequency plus and minus 1/2 of the bandwidth. Note that the bandwidth can be much smaller than the center frequency. Band pass filters are common devices with this type of frequency response. In a baseband system, bandwidth defines the 3 dB cutoff frequency, whereas in a passband application, both the bandwidth and the center frequency are required to determine the frequency response of the system. Channel 1 in yellow illustrates the output of a high bandwidth buffer amplifier, when its input is a sweep signal. Channel 2 in blue shows the output of a lower bandwidth amplifier under a similar condition. For this amplifier, the signal loss clearly increases with frequency. A frequency response analyzer graphically presents this loss. The 3 dB bandwidth of the amplifier occurs at a cutoff frequency of around 120 kHz. For a passband filter, however, the bandwidth is the difference between the two cutoff frequencies. This passband filter passes frequencies between 1.4 MHz and 3.3 MHz. Therefore, it has a bandwidth of about 1.9 MHz and a center frequency around 2.3 MHz. A signal is a composition of one or more sine waves. Sine waves of different frequencies, amplitude, and phase are the building blocks of any signal. In the frequency spectrum of a signal, these components appear as the fundamental and the harmonic frequencies. The difference between the highest and the lowest frequency components define the required bandwidth to process the signal. For example, an ideal square wave, regardless of its period, is composed of infinite number of frequencies, and therefore it ideally needs an infinite processing bandwidth. Channel 1 and Channel 2 display a sine wave and square wave of the same frequency. In the spectrum plot, the fundamental component of the sine wave in yellow, and the components of the square wave in blue stand out. For the square wave, the higher frequency components relate to its rise and fall times. With a low bandwidth setting, this oscilloscope filters the higher frequency components, and therefore results in slow transitions. A higher bandwidth setting reveals the true nature of the wave. To properly process a signal, the required bandwidth should be considerably larger than the highest frequency component of the signal. For example, a signal band limited to 2 MHz around a center frequency of 10 MHz needs a processing bandwidth that is much higher than 11 MHz. The bandwidth of a system depends on several factors and is generally limited by the component with the smallest bandwidth. For example, placing a 1 kHz simple RC filter in series with the output of a 1 MHz amplifier reduces the signal bandwidth through the circuit to about 1 kHz. A higher bandwidth often offers more flexibility. The various notes of a musical instrument are a composition of numerous high-frequency harmonics. And although the detectable frequency range of human ear is 20 Hz to 20 kHz, limiting an audio system to this bandwidth distorts the sound. That is the reason why an audio sounds different in a recording. At times the bandwidth of a system is intentionally lowered to zoom on a specific band of frequencies or to reduce noise. In digital signal processing, bandwidth refers to the system's maximum allowable data transfer rate in bits or bytes per second. It specifies the data handling capacity of a network. Higher bandwidth allows a higher transmission rate. Regardless of the application, bandwidth specifies the ability of a system to handle high-frequency traffic.